Zeros, multiplicity, and degree, Algebra 2 Common Core. So what exactly are zeros? This is coming off of chapters where we were factoring and solving to find zeros, and we just did quadratic formula, completing the square to solve for irrational zeros. So what exactly are zeros? Well, zeros are called zeros because they are locations on the graph where y equals 0. So we look for points on the graph where y equals 0. The other words for zeros, the term roots is what I use a lot, but really they are, sometimes referred to as solutions. And really what all of these things are talking about is x-intercepts. So what are the zeros of these graphs? Well, I can see right here I have one at -3. Sorry if the numbers are a little small. Here's -3, and here is 2. So the zeros on this one are -3 and 2. On this one also has a -3, and this one also has a 2. So the zeros here are the same. And what do you notice about this graph? What are the zeros? -3 and 2. And so what this is, attempting to, illustrate to you is that graphs can have the same zeros, but look very different. None of these graphs look anything alike, P of x, Q of x, R of x, but they all have the same zeros. And so there's not just one graph that could have these zeros, but notice that there's a lot of different things happening as far as graph structure goes. And that's really what this main chapter is about, polynomial graph structure. Why do they look the way they look? And why do they behave the way they behave? So I'm going to come back to this in a minute, but let me give you some definition stuff here. Multiplicity of a zero is the number of times that its associated factor appears in the polynomial. So what we're saying is how many times is it a factor? So for example, if we had something that factored to be x plus 3 and x minus 2, like if this was, f of x, that would have roots of -3 and 2. And then let's say we had a different function, g of x, that had factors of x plus 3, x plus 3, and x minus 2. And so like if we multiply this out, this would end up being x squared, so on. If we multiply this out, it would end up being x cubed, and so on. So these graphs are going to look very different, and yet they're going to have the same zeros, the same roots. But notice that I use this one twice. This would be a case where we would say that this particular function has a 0 or root of -3 with a multiplicity of 2. And what that really means is it showed up twice as a factor. When your highest degree is x to the third, that means you could have, as many as 3 real roots. And so, well, as many as 3 roots, period. Imaginary is included in there. We're going to talk about more imaginary another day, but if we're x to the third, we could have 3 real roots. 2 of those are the same at -3. And so multiplicity is how many times is that root's factor part of the polynomial. And then some interesting things happen when a root has even multiplicity versus odd multiplicity, meaning if it shows up an even amount of times. Like in this case, we would say that this root has an even multiplicity because it's multiplicity 2. Same thing for multiplicity 2, 4, 6, 8, even numbers. Whereas this root of x equals 2 just has a multiplicity of 1. So if it shows up from 1 factor or 3 factors or 5 factors, then it has odd multiplicity. And some interesting things happen. When you have even multiplicity, you get x-axis is tangent to the graph at that 0. And what we're really talking about is this case right here. The x-axis is tangent to the graph at 0. A tangent, if you remember back from circles last year in geometry, a tangent is a line that just kind of skims the circle or graph once. It doesn't cross it in 2 spots. Like that would be a secant. It's just hitting that one spot, so it's tangent to it. Tangents become really important as you get deeper into algebra, pre-calculus, and calculus. But the way we tend to refer to this as a tangent root kind of thing, a lot of times we call it a bouncing root. What does the graph do? It doesn't cross the x-axis, it bounces at the x-axis, where here it is a crossing root. It crosses the x-axis. This graph started below the x-axis, it hit the root, it never went above the x-axis, it stayed below it the whole time, so it's a bouncing. So when your graph has even multiplicity, it bounces. So it's a bouncing root. And really what that means is that it's tangent to the axis at that point. Now if you have odd multiplicity, it's going to cross the axis at that 0. So if you have 6 factors of one thing, like if we were to create a different function here, let me just use some space wherever I can find some space. Like if we had f of x equals, x minus 5 to the 6th, we would end up with a root of x equals 5. It would have a multiplicity of 6 because it came from 6 factors, and all we would see is the graph would be bouncing at x equals 5. It would not be crossing. Now, if I were to change this to the 7, an odd number, it would have a multiplicity of 7, and you would see the graph crossing the x-axis at 5, not bouncing at it. So even multiplicity bounces, odd multiplicity crosses. So even though all 3 of these graphs have the same roots, they're all very different. That I could tell that this is going to be an even multiplicity because it's bouncing. This is going to be an odd multiplicity, like maybe 2 of these, 1 of these, or 4 of these, and 3 of these kind of thing. The fact that it's bouncing in both of these spots means this is even and this is even. So this has 2 roots, both even multiplicity. That means there were an even amount of x plus 3 factors and an even amount of x minus 2 factors. Here, there's an odd multiplicity here because it does cross. And the flatter it tends to get as it crosses tends to be the higher the multiplicity. Same thing here. That looking at these, I don't know for sure what this multiplicity is, but this is probably multiplicity 2. This is probably multiplicity 4 because it gets wider. The higher the multiplicity gets, the graph tends to kind of flatten out at that spot. And it's not crossing more than one spot at these locations. It just gets really, really close to flat, and then it crosses and then comes back. But this has odd multiplicity because it's crossing, and then this again has even multiplicity because it's bouncing. So all 3 of these graphs are different because they have the same roots, but they have the same factors. They all have x plus 3 and x minus 2 as factors, all of these functions, but they have a different amount of x plus 3s and a different amount of x minus 2 factors. This graph right here is an 8-degree polynomial. And we want to list the zeros with the multiplicities. So what we see here is we have a 0 of x equals negative 15. We have an x, so negative 15, negative 10, negative 5, 0, 10, and 15. So that's a total of 6 roots, but we're degree 8. And so what that means is some of them must have a multiplicity of greater than 1. And we could tell that this is bouncing here, right? The graph is coming and bouncing off the x-axis, not crossing. So that means that that has at least 2, multiplicity of 2, because it's bouncing. It's crossing here, crossing here. Now, crossing doesn't mean it's 1. It just means it's odd. So there could be 1 of those, could be 3 of those, could be 5 of those. But that's going to be odd. That's going to be even. That's odd. That's odd. It's crossing, crossing. Here's another bouncing one. That's even. Since we're degree 8, that means we have 8 factors. And since there's 6 of them here, these 2 must be doubled. Now, again, just from the picture, I can't tell if this is 2, 4, 6, or 8. But it's going to have to be 2 of these and 2 of these because we already have 6, 7, 8 for a total of those. So the crossing ones here are multiplicity 1, like negative 15 is multiplicity 1. Negative 10 has a multiplicity of 2. Negative 5 has a multiplicity of 1. 0 has a multiplicity of 1. And then 10 is the other bouncing root, so that's another multiplicity 2. Again, don't think it's always 2 when it bounces. That just means that it's even. But if you know the degree of the function, you can figure out what are the odds of it being 2 or 4 based on how many roots you know you need to have and how many factors you need to have, kind of thing. All right, so then how about from an equation? How can we do that? Well, we know that from a graph we see where it's crossing or bouncing the x-axis to find the roots and the multiplicities. It's actually just as easy when it's in factored form for you, because looking at this x plus 1, x minus 5, that's a root or 0 of negative 1 and 5. And I only have one of each of these factors, so they're both just multiplicity of 1. Let's go over here to b. X plus 5 is going to give a root of x equals negative 5, and there's only one of those factors, so multiplicity 1. X minus 4 squared will give us a 0 of positive 4, and this is going to have a multiplicity of 2 because it's squared, meaning there's 2x minus 4s. It's x minus 4 times x minus 4. So since there's two factors of it, you're going to have that root show up twice. It's going to be multiplicity 2. And if we looked at this in our y equals in our calculator, type that into the y equals, you will see a crossing here, but bouncing at the 4. And then there's a root of 1/2 from this with a multiplicity of 3. And again, we'll see a crossing at that spot. It also wants to know the degree, but let me do the roots first. So then this one over here. Now 2x does give me a root. It gives me a root of 0 with a multiplicity of 1. X plus 4 gives me a root of negative 4 with a multiplicity of 1. And then this piece right here, x squared plus 3, I can't solve that and get something real. If I did, x squared plus 3 equals 0. Sorry about that. Just my speaker turning off. And so then we would want to subtract 3 and do the square root of it. You'd end up with plus or minus the square root of negative 3. And again, I keep saying I'm going to learn more about this, but this is imaginary. So what this particular example is showing us is we have two real roots, multiplicity 1 each, and then you're going to end up with two imaginary roots. And then this one's not factored, so we got to do a little work here. Just factor it real quick. Do some grouping, x squared, x minus 1. Take out negative 4. No, that's not going to work out. So this one doesn't look like it's factorable from normal methods. So what we could do with our worst case here, I'm getting to around 12 minutes, so maybe I'll do this in class, but we could use our calculator to kind of see these factors or see where the roots are from a table. But let me show you this one in class so you don't have too long of a video tonight. Last thing I want to do is what's the degree? The degree is basically add up the multiplicities. I see two factors here, multiplicity 1 each, so this one is degree 2. And if you multiplied it out, that means your highest exponent would be 2. This problem, I have 3 factors, but some of them have multiple multiplicities. I have 3 here, 2 here, and then 1 here when there's no exponent on it. So that's 3, 4, 5, 6, degree 6. And if you multiplied all this craziness out, you would end up with x to the 6th as your highest exponent. And then this one here, again, I only have 2 real roots here, and then I get a couple of imaginaries, but it is degree 4. So I'm going to get 2 imaginaries, 1 real, 1 real. And that does give me degree 4. It just means that I'm only going to see it touching the axis twice. And again, we're going to talk more about the imaginaries as we progress in the course. And then this one, take a look at that in your calculator. See if you could figure out the zeros and their multiplicities, and I'm going to talk more about that one in class because this video is running a little long. All right, see ya.